Um, well,
He has
kicking
to
off
get it
our
too, though.
afternoon
Great.
session.
I don't mind if they're heavy.
Wait, no, there is an echo somewhere. Okay, yeah, kicking off our afternoon session, we have Jayadev Athreya from the University of Washington, and he will tell us about local geometry of random geodesics on negatively curved surfaces.
Well, first of all, thank you very much for giving me this opportunity. It's just such a wonderful audience of folks. So many folks that I know well, and some I hope to get to know better. Thanks also for the really nice organizational aspects. The random breakout rooms. Hold on one second. The random breakout rooms were really nice, getting to meet some new people, and then having the breakout rooms after the talks. It gives you some time to think about kind of what questions you want to ask. With that said, feel free to interrupt at any point if you have questions about what I'm going to talk about. I'm very happy to be interrupted. I don't mind that at all. So feel free to interrupt at any point. Okay, so I'm going to tell a story today about, so I think to be very broadly philosophical for a second, a lot of dynamical systems and a lot of what we've seen today is the question about how much do various kinds of dynamical systems resemble IID random variables? So you saw a little bit of that even in Mark's talk. We're thinking about, we have various measures of complexity of a system, various measures of how complicated it is. Definitely saw it in Agnieszka's talk, where we're talking about, well, what kind of laws of large numbers can we have, or what are some things where laws of large numbers can't happen? And again, when you think about the shift on two letters, that's sequences of coin flips and prescribing various things that can happen with coin flips. We know how to do that. How can we make that work for dynamical systems? And then, Selma's talk, Khinchin's theorem, after all, is just the Borel-Cantelli lemma. Not just, it is a version of the Borel-Cantelli lemma. So a lot of what we're going to do, a lot of what we do in this field is try and say, okay, how much does our favorite dynamical system look like some kind of random process? But we usually do that with some kind of numerical measurement. So today what I want to do is, it's still math, there's still numbers around, but I want to do a kind of geometric measurement of randomness. So we're going to look at a geodesic on a surface, and it's going to wind around the surface. It's going to, with probability 1, it's going to equidistribute with respect to an ergodic measure. But we're going to look at sort of how it cuts up the surface. And the problem we're going to try and understand is, how does this long random geodesic cut up the surface? It's going to cut it up into some polygons. What can we say about those polygons? And can we say that this resembles some kind of recognizable random process? So that's the goal for today's talk. It's inspired, certainly by work of Mark's, work of Steve Lalley's, Moira Chass, lots and lots of people whose work has kind of gone into this. But today I'm actually going to be talking about work with Steve, Jenya Sapir, and Matt Wroten, and it's to appear in the Analyse Henri Lebesgue. The paper is on archive. And one of the things that will be a little bit tricky here is some of the measure spaces I'm going to deal with are going to be a little bit complicated. So please feel free to interrupt when I'm defining certain things. The intuition isn't so complicated, the precise statements are. Okay, so let's introduce our cast of characters. We're going to start with a closed hyperbolic surface, so compact hyperbolic surface. And we're going to start with a geodesic trajectory on the surface. So we have, forever and ever now, we have a fixed hyperbolic metric. So my surface comes with a hyperbolic metric, so I know what it means to talk about geodesics. So I start at that point with that little arrow, and then I just run my geodesic. And by the way, I should say, I have shamelessly, with permission, stolen my co-author's beautiful slides. Jenya made these incredible slides, and we were both giving talks about this at various times, and I was used to giving sort of chalkboard talks about this. And then Jenya made these amazing slides, and I said, can I please steal them? And she very generously let me do that. So all the work in these slides, certainly, and a lot of the work in the paper is Jenya's. So yeah. Okay, so here's a geodesic. As you can see, a typical geodesic kind of wraps around a bunch of times, it crosses itself a bunch of times, and it cuts the surface up into, ignoring sort of the very first bit and the very last bit, you get a tessellation of the polygon, of the surface by hyperbolic polygons. So let's go back just a second and say, what do typical geodesics look like? We start with we have the unit tangent bundle, that's parameterizes geodesics. GT is my geodesic flow. So what do I mean when I say take a geodesic? I say take an initial vector V, follow it around for some time. And of course, well, not of course, and it's a deep and beautiful theorem. For almost every, now we're going to talk about, since I'm talking about negative curvature, I can be very constant negative curvature. I'm going to say Liouville measure, measure of maximal entropy, everything's the same in this case, just hyperbolic measure, the natural measure on the unit tangent bundle. And any, okay, there's a small, any continuous, let's say, F from T1 S to R, really any L1. So I should be a little bit more careful there. I just ran out of room on the slide there. So now you average your function along the geodesic, and you get the average of the function on the surface. And so here, notice lambda, I have not normalized lambda, so I put this normalization on the outside. Okay, so 2 pi is the tangent bundle part, area is the area of the surface, which is, depends on the Euler characteristic of the surface. Okay, so it's spreading out completely evenly. That's a kind of, we're using this observable, or if you like Ignatius' talk, we're looking at a convergence in the space of measures, right? We're looking at these orbit measures. So for instance, you start in, you have some neighborhood in your unit tangent bundle. How much time you spent in there is proportional to the volume, right? That's what this theorem says. Time averages converge to space average. I always like when I'm giving a dynamics talk to start with Birkhoff, because I mean, it's really an amazing, amazing theorem. So not a nice person, but an amazing theorem. Okay. All right. So now we can actually, it's not so hard to sort of conclude from this that you take this very long arc and you're going to, eventually you're just going to lose all topology, right? All the complementary regions of this geodesic are not going to have, they're going to be simply connected. They're going to be polygons, right? You're not, okay, of course, if you took, say, some sort of simple closed curve, you could just run along that and cut the surface up into 2 pieces. But in general, when your surface is kind of moving around all over the place, when your surface is moving around all over the place, when your geodesic is moving around all over the place, it's going to cut it up into simply connected regions. And moreover, it's maybe not so hard to convince yourself from, say, Birkhoff, that let's say you zoom in on some neighborhood U, and you look at how this geodesic, after some very long time, has kind of crossed you. It's going to be kind of unbiased as to how it comes into this region U, right? It's going to come in kind of from all directions. And so, that's just something to keep in mind as we go on. So we get a kind of a sequence of, again, I'm going to ignore this kind of initial segment before the first crossing and then this last segment. We get a sequence of kind of tessellations of the surface in the hyperbolic polygon. So they get kind of more and more complicated. So this arc gives you these tessellations. The question is, how does it cut up the surface? And of course, this is not a very well-posed problem yet, but you can make it well-posed by saying, for instance, okay, there's going to be some hyperbolic triangles in this tessellation. There's going to be some hyperbolic quadrilaterals. There's going to be some hyperbolic n-gons. Okay, so there's a certain number of there's a certain number of polygons. What proportion of them are triangles? What proportion of them are quadrilaterals? What proportion of them are n-gons? I think this is actually a really beautiful question. I really like this question. And it's a question, I like it also because it's addressing the kind of, this thing, okay, how much does this geodesic resemble some sort of random object on the surface by making it a kind of intrinsically a two-dimensional kind of question. So you could also ask for things like, how long are the edges? What are the angles between, what are the angles of these polygons? And of course, you should probably right away say, how long are the edges? Don't be silly. All the edges are getting very, very short, right? You're just kind of cutting everything up. Of course, what we mean is how long are the edges when appropriately rescaled, let's say. Okay, so we have some random arc, length L, and we get this tessellation, which we're going to call T sub L. We pick our arc at the start. And it has V of L vertices. Now, the number of vertices is already a non-trivial kind of question. That grows quadratically in L. And that's not, to me at least, that's not obvious. So let me give you a very silly, well, not silly, but a reasonable heuristic for this, which is full of lies. Okay, so I'm warning you, what I'm going to say is full of lies. I realize I keep looking up at my TV, where is not where the camera is. So when I look up at the TV, I look like I'm staring off into some ill-defined point in space. Okay, I'm going to look at my laptop, but the pictures are nicer on the TV. Okay. So imagine your length L arc as a sequence of L length 1 arcs. Okay. Now, if I just have two geodesic length 1 arcs on the surface, there's some positive probability that they intersect, right? Just because, intersecting is kind of an open condition in tangent bundle across tangent bundle. Okay, so if I threw L independent arcs down on the surface length 1 arcs, then, L squared of them, you would get L squared intersections because there's L squared pairs, and the probability of any pair intersecting is positive, so you would get L squared. That's not at all a proof, right? To make it into a proof, what you need to say is something like, well, the arcs at the very beginning and the arcs at the very end have almost nothing to do with each other. They're kind of almost independent. But that's the kind of argument that this crowd should like, hopefully. So anyway, so there's L squared of these guys. That's one question. And that was due to, that's due to Steve Lalley. So now you have this length L arc, and if you have a region of kind of fixed size, you're going to cross it kind of L times, because each time you're going to kind of pick up a definite amount there. So here's another explanation. So you have different crossing angles, and implies that kind of most of these pairs intersect. Right? That's another kind of way of seeing it. L squared intersect. So in particular, okay, so now we have all these complementary regions, they're polygons, and let's say we have V of L edges, E of L edges, V of L vertices, E of L edges, and F of L faces. And then, of course, if the vertices grow like L squared, so do the number of edges and so do the number of faces, more or less, right? The number of vertices, each vertex has, a certain number of edges. Each edge has 2 vertices. So the number of edges should be half the number of vertices. And then by Euler's formula, we fix the genus once and for all, the number of faces should also be the same, right? Because V minus E plus F is constant. So if V and E are both growing quadratically with different quadratic things, right? F should be half of E as well, right? Because we want V minus E plus F should be a constant in L. So V minus C plus F is chi, and then the number of edges is 2 times the number of edges, 4 times, edges, each edge touches 2 vertices. Okay, so now let me give you, I'm going to resist giving you the very precise statement. So let me first give you the kind of vague statement. The vague statement is that with probability 1, the statistics of this tessellation approach those of a Poisson line process. It's actually a slight, so this is a probability 1 statement, but it's going to come from a statement about convergence and distribution of a certain process. What does this mean, though? What are some consequences for this? I have to tell you what a Poisson line process is too. Don't worry, I don't believe, I didn't know what a Poisson line process is before I started thinking about this. So I certainly don't expect this to be a common piece of knowledge. For instance, the probability, the proportion of n-gons approaches a number tau sub n positive that you can actually compute. So as L goes to infinity, tau 3, the proportion of triangles, is this very interesting number, 2 minus pi squared over 6. About 35% of the polygons that you get are triangles. Tau n in general is not so easy to compute. You can try and do some numerics, but what is kind of interesting is summation n times tau n. You can think of tau n as a probability distribution. The expectation of it is 4. That's maybe not so surprising. You kind of expect your typical guy to be to have 4 sides. Now, a question I don't know at all, and I would love for people to think about is there some kind of large deviations result? Do you always kind of cluster around 4? What do the kind of tails of this distribution look like? This is all, it's kind of not so easy to compute. But, and then there are also limiting distributions you can write down for the edge length and for the intersection angles. Appropriately renormalized, of course. All right. Okay, so And the angles, in fact, are kind of independent, and the probability distribution is kind of 1/2 sine theta. So you expect to see kind of, yeah, this is, you can play around with this a little bit. Let's see how I'm doing on time, 12:40. Okay. So in particular, you expect to kind of, sine theta is basically the density near zero is like theta. So you like larger angles better. So you don't expect to see a lot of tiny crossing angles. You expect to see more, reasonable crossing angles. The times of self-intersection behave like a Poisson point process of intensity 1 over area of S. All right, I've said a lot of, things, but maybe I should, yes.
Can I actually ask a quick question?
Go for it.
Maybe you're going to talk about this later, but this 2 minus pi squared over 6 is like very suspicious to me.
It's incredibly suspicious to me too. It's a weird integral, and it's an integral where Li2 pops up. I wish I understood the why of this better. The why of this is a really, really good question.
Okay.
But it's universal for all these surfaces. It's, yeah, I don't have a good explanation of the why of this pi squared over 6, even though I would love to.
Okay, thanks.
Yeah, of course. Okay. So let me actually, yeah. So, right, so again, very, very, very vaguely and very, very philosophically, right? Birkhoff says, oh, you look at this long geodesic and you kind of look at these segments and they're kind of these random collections of lines. Right, that's very vague. But let's talk about what a truly random collection of lines in the plane might actually look like. So there's lots and lots of choices of you can have lots and lots of random processes which give you a collection, give you probability measures on collections of lines in the plane. That's what you'd mean by a random collection of lines. You want a probability measure on the space of collections of lines, for instance. Okay. Well, maybe we want to impose some conditions on those lines. Maybe we want some kind of local finiteness, right? We don't want, in any neighborhood to have infinitely many lines in there. So here's what we're going to do. Here's our method. We're going to draw lines at angle theta I and distance Ri from the origin. So what we're going to do is we're going to take a line at angle theta I, and then we're going to take the distance Ri and we're going to draw the perpendicular through the line at angle theta I. So the dashed lines are the lines that I drew, and then I go out distance Ri on them, and then I draw the perpendicular to those lines in the solid. What we're doing is we're taking now our theta i's, what we're going to do is we're going to take them IID, uniform 0 to pi random variables. So we're going to pick, you're going to go into a room and just generate a sequence of angles, and we're going to draw these lines. And then I'm going to choose these. Actually, I should say the way I've written it, I want the Ri's to all be positive, because my theta, otherwise, if you don't want your Ri's to be positive, you could take your thetas to be uniform in 0 pi, and then you could go negative as well. But let's say I want to do positive, so that should be an R plus. And we take them with a Poisson process. That's a Poisson process of intensity lambda. So for instance, the probability that you have n Ri's in the first L is given by lambda L to the n over n factorial e to the minus lambda L. So again, to a probabilist, what do? I tell my one probabilist to go into a room and generate an IID sequence of uniform 0 to pi random variables. I tell the other probabilist to go into a room and generate a Poisson process of intensity lambda. And then I go out distance R1, where R is my Poisson process, along line 1, and then I draw the perpendicular. And that's my first line. So the dark, the heavy lines, not the dotted lines, are the lines in my process. The dotted ones are not part of my process. They're sort of auxiliary things I used to generate my process. That's what a Poisson line process is. That's a perfectly nice measure space, right? It's Poisson process of intensity lambda, countable product IID 0 to pi random variables. If you want, you can generate this using, say, one uniform random variable. You can generate this process. This is still a standard Lebesgue space. There's nothing scary about this random process. Okay, but this is a crucial thing. This definition is crucial, so I want to take a second and ask if people have questions about what a Poisson line process is. Okay, everyone's happy with the Poisson line process. You could also ask me later if you don't have a question right away.
My only question here is why you would pick the Poisson distribution over other things, maybe. Maybe I missed you saying that, but.
No, that's actually an excellent question, and I haven't said why. Because you're going to get isometry invariance of this measure. So this is a measure on the space of locally finite collections of lines in R2, right?
Yeah.
And then, so of course, so any group that acts on R2 will then act on this space of probability measures, and this measure will be invariant with respect to, let's say, the isometry group of R2. This is translation invariant. So this choice of the origin was completely irrelevant, actually.
Oh, okay.
Yeah,
Cool.
and it's a translation invariant, and it's rotation invariant. It's reflection invariant too. But yeah. So there's absolutely a good reason to pick the Poisson thing, and I didn't say why, but that's why.
Okay, cool.
Yeah. I should say, and I'll mention this a little bit later, a really good place to learn about this Poisson line process. There's was the PhD thesis of a mathematician named Richard Miles, who worked in geometric probability. He stated and proved a lot of assertions about the Poisson line process. It's not always easy to find his thesis, and not all of the proofs are written down in complete detail. They're written down in complete detail modulo basically some exercises in probability theory. But what we've done is in an appendix to our paper, we've tried to write out as sort of full proofs about whatever we're using about the Poisson line process as well. So you can look at our paper if you want to just learn about the basics of this process as well. And again, these invariance properties that we use, we talk about that there as well. Okay. So now you get so you take your Poisson line process, you also get a tessellation of R2. And by the way, this is really not a lie of a picture here, right? Like the process is locally finite. In any fixed neighborhood of 0, we are only seeing finitely many lines. We're not getting a lot of lines near any particular point, right? The distance I'm going out is growing exponentially. Like the RIs are getting further and further away. So, like I said, in this PhD thesis of Miles, which is now almost 60 years old, you get statistics of frequencies for n-gon, side length. So that tau 2. Ethan shows up in this paper first. Side length, angles, etc. on the Poisson line process. And what we do is we show the statistics that we get on the surface are the same as that for a Poisson line process on R2. Okay, that's our result. And in fact, so how do we get our result? What we do is we say, this is all about local geometry. So we say, take your length L arc, and then what we do is we take a ball on hyperbolic space of size lambda over L. And now I don't know if I'm going to make people who like negative curvature happy or unhappy with this, but okay, if L is extremely large and this ball is very small, you can't really see the negative curvature anymore, right? A tiny little ball looks flat, right? So it's okay to think about this thing as a ball in the plane, right? The exponential, we just sort of identify using the inverse of the exponential map, and that doesn't really distort things very much. So this geodesic crossing, well, here it doesn't look very tiny, but L is getting bigger. My ball is getting smaller and smaller. Okay, that's the smallest. And now what I get is I get a collection of lines. I cross this ball of size 1 over L roughly, L times lambda over L times in my geodesic of length L. So I get roughly lambda times. And so I cross it kind of a fixed number of times. Lambda is a parameter, just a positive parameter. And so now what I'm going to get is I'm going to get some picture that looks like lines, Euclidean lines in a Euclidean disk. And so the actual theorem is as L goes to infinity. Okay, now this is not at all a precise mathematical statement, but we say the tessellations of these, so you fix whatever x you want, you look at these tessellations and they kind of approach that associated to a Poisson line process intersected with a ball. What do I mean by that? There's actually a subtle convergence and distribution statement here. It's a statement about our convergence in measure here. So it's a statement about the measure of the set of geodesics so that when you intersect with this ball, the pattern of crossings you get, you look at the probability that you would get that minus the one associated with the Poisson line process. Anyway, I don't want to go into full detail about that. There's a quote in our paper where we say something like the probability spaces we deal with are quite complicated. So we spend like 3 pages carefully defining them. Since this is a big audience talk, I don't want to do that. So please bear with me in being slightly sloppy. Just for the experts in the room, this is a convergence in distribution statement here that leads you to other statements. But the statement is that you approach a Poisson line process. And in particular, even more fun, you take 2 points, and these points, these are statements for every x, for every x and x prime, and every scaling lambda, so you fix lambda. Then these tessellations of a random geodesic, approach an independent pair of Poisson line processes. So one point has no idea what the other point is doing, which again should not be too surprising for those people who think about hyperbolic dynamics, right? It's why should a shrinking thing over here have anything to do with a shrinking thing over here? Okay, so once again, let me give you lies. An incorrect but illuminating idea. Again, we're going to cut our arc up into segments. Let's assume the segments are all independent. Lie. The probability that the ith segment crosses, I'm missing a parentheses. This size of lambda over L is basically C over L, some constant over L. And now we have the binomial distribution, right? So you have independent and independent trials. So the probability that you get n of these guys in there is n choose L, probability to the n, 1 minus probability. So I have L trials, sorry. So it's n choose L, L choose n, C over L to the n, that's the probability, then 1 minus C over L to the L minus n. Right? Okay, but think back to your introductory probability class. What does binomial, like if n times p, if n times the probability is kind of converging to a constant, if you have a sequence of binomial random variables with np all kind of hovering around something, what does that behave like for n large? Of course, maybe we all remember the central limit theorem where it says you do, binomials with more and more trials, they look normal. But what if you're also changing the number of trials, but also the probability at the same time? So n times p is a constant. Anybody remember what that behaves like? My father, who's a probabilist and is watching this from his chair, has given us the answer, but I don't want a probabilist to give us the answer. I'd rather have a dynamicist. Anybody remember their basic probability class? What does binomial approximate? Uh-oh.
Hypergeometric?
No, Poisson.
Oh, Poisson.
Yeah, binomial, if you fix n times p, binomial approximates Poisson. Hypergeometric is actually a very interesting distribution, which I'd love to see more of in dynamics. But you can use Stirling's formula, for instance, to do this. This, is you get a Poisson distribution of kind of parameter c of lambda. If you can plug this into, say, Stirling's approximation. So you get this Poisson approximation, and that's where our Poisson is kind of popping up here also. Of course, now let's confess to all the lies. So, but I should really say, despite all the lies back there, really the heart of this proof, so this proof can be summarized in 2 things. The probabilistic idea is that Poisson approximates binomial, or binomial approximates Poisson. And then the dynamical idea is symbolic dynamics. Okay. So length 1 subarcs aren't really independent. Hopefully 2 subarcs far enough apart are close enough to being independent. Random geodesic forgets its past. Of course, we've seen equidistribution results from Osama, which hiding behind those was exponential mixing of a certain flow. And so here, what we're really, there's exponential mixing hiding here. And the other big thing is that one thing you might really worry about is, okay, yes, you're saying that these, if you take a long time between passages through, those are kind of independent. But what if you have a geodesic that leaves and then comes back right away? That might screw up your independence, right? Those guys are not actually going to be independent. Those are going to be very, very dependent. But what you do is you have to bound that probability that the return, and that's purely kind of geometric, that if your geodesic leaves a small ball, it doesn't want to come back right away. It's unlikely for it to kind of want to backtrack. And now let me draw some pictures, or let me use Jenya's beautiful pictures more accurately to indicate kind of an idea that really goes back to kind of Sullivan. Or even further probably. So we have this fundamental domain. We're going to tile it. Well, what I'm going to talk about now. So there's a counting result to Sullivan. The coding I'm about to describe goes back to say Bowen and series, or Adler and Flato, or if you want to do the modular surface, you have connections to continued fractions and Morse. But really, I should say the word names of Bowen and series here. That's maybe the most crucial ones to say. So we choose these fundamental domains. We tile the universal cover with these fundamental domains. So this is I've drawn in the Poincare disk. And then a geodesic trajectory is a sequence of edge crossings. So of course they're looking smaller, but they're not really. And most sequences of these things, you get a geodesic, right? You're going to get a geodesic, vice versa. Unless you kind of pass through a corner, you're going to get this nice coding. So you get a coding of the geodesic by kind of a word in these, in these fundamental. FD is not finite dimensional; it's fundamental domain, in fundamental domain edges. And then hopefully these crossings kind of far enough apart, hopefully this thing behaves enough like a Bernoulli shift that these guys are going to be kind of independent. And, so these guys that are passing close to each other, after a while, they're wildly passing through different sequences of fundamental domains, even though this is all negative curvature at work, right? I mean, things hang out close, but then they run away from each other really, really quickly. And now what we're going to do is we're going to use edge crossings. I see there's a question in the chat. Yes, I can, of course, wrap up in 4 minutes. 12. Really? Okay, yeah, 5. It was 12:25 to 1:05, I thought, right? No? Was it? No? 1? Okay.
Oh, including the question time.
Got it. Okay, let me wrap this up then. So here's the crucial idea. Crossing a small ball corresponds to a word of length log L. And then you get special subwords that tell you how you cross the disk. There's a collection of special subwords. And these disk crossings, they occur kind of far apart from each other. And this is the kind of Sullivan-esque picture. You have these small balls, you have this log L length segment, and you cross them kind of far away from each other. And yeah, so here are some pretty pictures. The measure of arcs returning quickly goes to 0. You have the sequence space. This is the part that's more familiar to the dynamics audience. So maybe I just go through it very quickly and just sort of flash it up to you. By infinite sequence, you have these crossings. You have a roof function, which tells you how long you takes you to cross a fundamental domain. And you have your symbolic parameterization by the shift map and the suspension flow. You get a semi-conjugacy. And we just do all of our work here. And we use the fact that we get a Gibbs state, that we have a Gibbs state. And we use the dynamical properties there. And maybe just to wrap up, the theorems hold for variable negative curvature. Compact, I should emphasize, compact and variable negative curvature. Again, you can use the same similar symbolic dynamics. Interesting question would be, what if you take longer and longer closed geodesics or a random closed geodesic? It should be true, but we don't have a proof. What about geodesics that other geodesics that don't equidistribute in the surface, but maybe they still fill the surface? What can you say about those tessellations? What about typical geodesics with respect to a singular flat metric? And then also, very obviously, what about non-compact negative curvature? Even the modular surface, it's open. So the non-compactness makes life very difficult for us. So this is a good place to stop. Thank you guys very much for the opportunity, and I will stop here.
All right, everyone, let's thank Jayadev. And we've got time for a question or two if anyone has any.
ask a question? Could you say a word about the difficulty with non-compact spaces, or is that?
No, it's I mean, it's what you think it is. It's the minute you don't have this this finite symbolic coding, a lot of the methods are much harder. Now, maybe using some stuff of, say, Butzi-Sarig or some of the new methods of understanding countable state space shifts, we can, you know, we need this thing to be a Gibbs state. We need, the other problem is, you know, that we need to, again, understand these no returns to small things. And I don't think, I mean, I think it should be true, but we'd also need to understand which kind of polygon the cusp lives in, right? Like, and so there'd have to be some understanding there, and that, you know, that region. So yeah, there have to be a slight change maybe in the statement where you sort of deal with the cusp in some way. I do think that the same result basically should be true. If you take a point which is not the cusp, you know, cusps in rank for hyperbolic surfaces are not that bad. You don't hang out in them very much. There's only kind of one way to go into them. You know, we're rank 1, things are good. So it should still be true. It's just the methods are, also we got tired. You know, maybe it's possible, but we also got tired.
Thanks. Yeah.
Okay, if there are no more questions right now, like Jayadev mentioned at the beginning, you can formulate your questions and ask him more things at 3:25 in a breakout room. So let's thank him again.